We extend my sincere welcome to our school dean, Dr. C.V. Subramaniam sir, who is the backbone for this type of all activities in the department. So we welcome our HOD sir, architect N. Ramesh Babu sir, who is always encouraging the staff and the student to initiate this type of seminars, workshops, etc. for the benefit of students. So we are honored to welcome the Lorry Baker of Thanjavur, Engineer Rajendran sir, who is icon for cost-effective construction techniques in Thanjavur area, also having rich experience in engineering and architectural designs, particularly temple design. He is also role model for many young engineers and architects. So we also welcome to all faculty, students and participants for these events. Thank you. Thank you all.
Thank you, ma'am. I would like to take this opportunity to introduce our special guest, Engineer Er.S.Rajendran sir. Today's research person, Engineer Er.S.Rajendran sir, has an experience of more than 47 years in the field of construction. He got graduated in BB Civil Engineering from REC Trichy and got his postgraduate diploma in valuation. His professional experience extends from site engineer at Kalpakkam Atomic Power Station, assistant engineer in Tamil Nadu Highways Department, to civil engineer consultant, valuer, and specialist in cost-effective technology and native engineering. He is also associated with various institutions as visiting faculty, including PMIST and NIT. And he is an active member of Heritage Screening Committee, Hindu Religious and Charitable Endowments, and Government of Tamil Nadu. He was the chairman of Technical Committee of a Builders Association of Tamil Nadu from 2004 to 2006, and he has also served as the vice chairman of Institution of Valuers Tiruchirappalli branch twice, and he has also been the vice chairman of Executive Member Committee since 1987. And he is also the former state president of FAZET, which is nothing but Federation of All Civil Engineers Associations of Tamil Nadu and Puducherry. And he has received innumerous prestigious awards, including Mamannan Rajarajan Award from the Government of Tamil Nadu, Award for Excellence in Cost-Effective Engineering received from the Governor, Dr. K. Rosaya at that time, and also Award for Exemplary Performance as Consulting Engineer from Honorable Governor of Tamil Nadu. And he has also received Lifetime Service Professional Excellence Award, which was given to him by, again, the FACET, which is the Federation of All Civil Engineers Association of Tamil Nadu and Pondicherry. And he was given Mayan Award in 2014 for perennial achievement in the field of construction by Vista India Communication Institutes of Chennai. He has also presented many papers and publications in various institutions and associations, and he has conducted many hands-on workshops on cost-effective technology at various institutions across South India. With these few words, I'm very happy to hand over the session to our special guest, Engineer Er.S.Rajendran sir. Thank you.
Hello. Good afternoon to you all.
Good afternoon, sir.
Good afternoon, sir.
I'm actually, the topic given to me is decoding the basics of structure. Right. It is an interesting subject. It is, I'm going to deal with the basic principles in architecture and engineering. How we do it, what is the, how it is done, and how we have to assume certain things. All those things I'll be explaining. I'll be explaining with a lot of photographs also. And whatever said and done, I come from a place that is Thanjavur, where the greatest hello. So, are you able to see the screen? Anything there? The title? Yes, very good. Fine. See that. I'll start from the human species, where they, you can call it Stone Age, where they lived in caves. Then later, once they started in the caves where the animals were living, they chased out the animals and they lived inside. And from there, once they started moving out, they started constructing tents, and then something using foliages, the wooden struts, all those things. And it went on. You could see there is a support. See, that time itself, they have that engineer. See, my cursor goes near the bottom of the shed, the tent. where you could see the heavy weight. You know why they keep that heavy weight? One is the wind may blow this, another one due to force, there's a lateral movement, this horizontal thing will come out so that they've fixed the bottom. The principle of what we say, anchoring the foundation. So that itself that they have started. So then once they started moving, the invention of wheel came. Once the invention of wheel came, the whole thing started very fast, very fast. So their movement and related with their construction activities, they were what according to the conditions of the site, they started using that. So like this, see, this is a broken granites they had used to construct something like. So this is an inspiration from the cave. This is an inspiration from the cave. This is see, one thing you should understand. On those days, everything was done by compression members. All should differentiate between a compression member and a tension member. See, a structure normally, whatever be on the earth, it is pulled towards the center of the earth due to gravitational pull. We call it G. Due to that, and if the soil resists, so it stands on that. The soil is not resisting. Suitably, you have to design the foundation and do it. And what the whole thing is like compression only. It is pulled towards it and it stands on that. The basic principles of that is another one. Our forefathers have followed post and beams. We'll talk about it later with some examples. I'll show you that also. See, this is how they went in for the detailing of the tents by using poles, bamboos, all those things over that foliages they placed. See, this is how they started. The form itself will resist. That's from here only we started going in for arches. See the form, it's a curved form. Look at this. Whatever weight comes on it, it is transferred to the ground. It is transferred to the ground. And initially they went for this something like a triangular one with a ridge roof. I mean, we can say pitched roof, we call it pitched roof, and that will have more load. But once it is a curve, it transfers smoothly. Here the pitched roof will, this end columns are in between whatever you give trusses, that will have the load transferred to this point. So instead of that, this curves very smooth, it ends up here. Like this next one. See, from there, once they started constructing tents, then using animal skin, all those things, and tying it to the ground with a guy rope, that they call it a tension member. And this is, there will be a pole in the middle. That pole will take the total load of the skin, and when it is pulled, the string is at the tension and the skin is at the tension, the skin, animal skin. And you have a completely projected inside, you could see a tent. So that's how it started. And gradually, when it started thinking of carving from the rock. See the whole rock. See, this is a beautiful thing. Whole rock, it is in Mahabalipuram. See the whole rock. I'm going to show you a lot of examples only in and around. I'm not going in for any foreign thing. See, we have so many things in our own place. So let us see that now. See, this is a rock. From this rock, they've removed these particles inside. That's a negative zone, you call it. So remove that, you have to think twice. You have to think many times. You should have a proper imagination and what it will be after carving, and what is the distance you are going to give. All those things you have to do it. You have to do it. So this is example, excellent thing. See, before this, the rock would have been from here. First they carved the rock and they have given the shapes of pillars, and that pillars also from the top of the line, Yari they called it. It is another form of line, and over that they had the motif. This is a Pandya style, Pallava style, and later Chola also took this. And see, in there, after the column, there is a space. See, you could see a person standing, and there is a space. So they had planned everything. Before starting this, they had conceived what to do and how to do. The negative spaces, they've removed all the negative spaces. And here, being a whole thing as a monolithic piece, whatever you remove, nothing will fall. So that is one advantage of carving. And you can completely, the stones, the pillars are not at all necessary for this, but still for the aesthetic reasons they have given this, and this is how they carve it. See, by carving, what they do for carving, see, look at this. You want a corridor like this. First, the whole thing, they'll find the depth, what depth the rock is there, without any problem, without any cracks or anything. And they'll cut like this, small, small pieces. And then inside, they go through this lane. See, another stone, 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 one by one pillar, pillar like that. See, they'll reach this till the length of the rock, and whatever the plan they had it. See, after the pillar, you have a space. After the pillar, you have a space. Can you see the space behind that? And all this are negative space. So you must conceive before starting the work, and then carefully go step by step from here to this column, from here next column that. So as you go, you have to maintain the distances, and then distances, and then the height, volume, everything they've seen it. So this is a total conception of the space and volume. So this itself, and this is complete, the whole thing is a solid material. Once you remove it, no load comes on this. No load comes on this. This is only a supporting piece. It's not a supporting piece, it's a partition. That's all. So even if without this column, the surface will stand, because the rock, it has got so much of rock, all wrong. So this is how they started doing. See, some of this, you are muted. See if there is an echo. Are you getting that echo, or you are getting the clear voice? My side, there is a lot of echo. Hello? Hello?
It is clear, sir.
Are you getting any echo?
Not now, sir. Initially there was an echo, now it is not there.
Now, not now. Okay.
Yes.
Doesn't matter if I have it. Okay. See, this is another column in the front, how they have cut it, and they have scooped out. See the cave-like thing. It goes on like that. And mostly this is not done for residential areas in India, especially in this part of India, that is Tamil Nadu. They have done mostly used for temples and other things. How many of you have visited Tirupparamgundram Murugan temple? It is totally a carved temple. From road it goes inside. So like that we have few temples carved. And this is also, these motifs represents the, the type of architecture it is. See, this is Mahabalipuram. Here also, the stone, the rock must have been at this level, top level, full, or here it would have gone like this, curved. And they have marked this from top, the plan, and they know what depth it has to go. And the depth also they've calculated, and they have started carving from top. You have to come reverse.
So this is a very tough thing. You can see some of the artists, even the sketching artists, pencil sketches or anything, they don't start from the beginning, an eye or a head or something. They'll start somewhere at a part of the body and then end up with that. So like that, the talent, this is a pure talent, and they had so much of skilled persons. The removing the negative zone, see the spacing between this, spacing between the two radhas is highly, I mean, they had calculated, anticipated. See, the crown of that is here, but it is outside. It will be from center line, it will be about 6 feet, 6 feet that side, about 12 feet at the bottom. So that calculation they should have made, and from 12 feet to another body, that should be about 10 feet. So all those things you have to calculate and do it. Being a monolithic material, there is no point of it. There is no need to worry about either compression or tension. So they just removed it. It is nothing but negative zones have been removed, and you see that beautiful projection. See, this another mural, huge mural in that. This mural also, they have done the water flowing also. Whatever water gets stagnated at the top, that flows through this and comes down. So this is another beautiful mural. And this I have to explain only in sight. See here, the continuous rock cut things are there. This is another tiger cave. This had come in many fairs, government fairs, entrances. This is the whole thing. They have done it in plaster Paris, and there'll be an entrance of about 15 feet by 15 feet. And you can, the scale was so big, you could see a huge this replica of this. And they have done a stone finish also in painting. So this is another beautiful work by Pallavas. And at the same time, let us think about, let us see something in Pune, Karla and Bahaj caves, where it is on a rock. They have carved it. Here, the another beauty is 2 floors. See, 1 floor here, another floor. The floor thickness will be very thick. So that's why there is no column outside. Nothing. It is not buckled. So even here, they have done it something like a woodwork. See this. They made the columns. Negative zones are removed. Again, see why I am telling you, why I am showing you this. I'll be coming to the exact what post and beams section. So you just see. I'm taking you around to see what the things are existing. See here the elephant. See, it is cut from the rock of this thickness. So see that entrance. It's something like woodwork, but it is rock, made out of rock. And imagine now we have very powerful electrical lamps and air conditioning system. Inside those days, they were sweating, and it used to be pitch dark. They had done all these things. In the daytime itself, it will be very dark inside. So against nature, they had worked. See the type of work, what they had done it. See, see the stone pillar has been broken. Vandalism. See here, here. This continuation is broken. See the elephant's trunk. So like this, still the structure stands. It won't buckle. Even if this supports goes, nothing will happen. It will remain like that. See, all these things are ASI control, Archaeological Survey of India. So they control it, and that's why the broken ones are not repaired. They don't allow repair. They want the the actual thing to be remain as it is. See the rocks here, Ajanta cave, Maharashtra. You would have seen lot of photographs of Ajanta cave. Inside you have vegetable colored paintings. So this is another thing, example, the human achievement. Similarly, in Arabia, this stone is little bit soft, not like our granite. There they have carved, they have made houses and such. See, this is another in Bali, Goa Gaje. This is a temple cave. Inside, outside rocks are made into a lot of patterns. The facade is decorated with a lot of motifs, and that reflects their culture and their tradition. This is how it is done. See, another in Turkey. See the height, the human scale. This will be about nearly 50 feet. And in this, they'll have a staircase inside. They have houses, rooms, and all the facilities. See, this is. And Jordan, see the rock, rough rock adjacent. See how they had done it, dressed it, and made it to them. Now coming back, so I have taken you around and shown you how the skillful people were. They were able to carve and make out a lot of spaces and shapes. Here, this is another. How many are able to recognize this? This is one of the greatest, greenest building in the world. You know what is green building? This is one of the greatest greenest building in the world. See, this is a big temple. We call it Avudayar Kovil. So this is see the plan now. This is a sanctum sanctorum. On this, there is a tower. Normally, the biggest tower will be in the main entrance. That we call it Rajagopura. Here the Rajagopura is reverse. Rajagopura is small. The sanctum sanctorum, we call it Vimanam. That is taller. So the first entrance, second entrance, and this is main temple. In between there is a Nandi Mandapam. This is important. I am going to deal lot of structural elements from here. So this is another view of the temple from the back side. Now coming to the plan and section. I think most of the architecture students are familiar with the plan and section. Look at the plan. The temple is 60 meters height. You take a radius, and the radius will cut at this point. Make this as a side of a square. That is 120 meter. 60 meter height and 60, 60, 120. So 120 by 120 square, and connect the diagonals. Where the diagonals meet, that is the center point of sanctum sanctorum. See, this is a connecting corridor, and this is a Mogapu Mandapam, big Mandapam, and this is another square. Make another square 120, and the diagonal meets at the Nandi Mandapam. And this is the second entrance, Rajarajan Thiruvoyal. And this is the Keralandagan Voyal. See, there is a modular coordination. This is 1, 2, in this half, that is 60 meters. So 300 meters by 120. And the combination is 2.5 squares. And the diagonal meets at a point of the inner side of the sanctum sanctum. I mean, not sanctum, the main entrance. Rajagopuram, small size. Look at this. See, the modular coordination was done 1,000 years back. That when they never had calculators, laptops, or desktops, all those things. No mathematical aid, it's equipments. See, coming to the subject, as we said, the load. Whenever a structure resting on the top of the earth, it is pulled towards the earth, core of the earth. That is gravitational pull. And now the structures are very tall. See, when 10th century, the 60-meter tall Perudayar temple was the tallest, second tallest at that time. So we had the credit of constructing a second tallest building 1,000 years back, second structure. And I just remind you, the total load is transferred fully. And it is transferred in a foundation, something like a raft. The raft is going to be the whole plan of the temple. That is what we call it, raft. And the raft is what we do in RCC. Reinforced concrete is used, and the thickness, the depth will be about 1 meter or 1.5 meter or 2 meter. And this whole thing floats. If the soil is bad, hello, hello,
Sir?
yes, there is a disturbance. Hello, are you
Sir,
able
you're
to
audible, sir.
audible? Okay,
Yes,
I'll
sir.
continue.
Yes, sir.
See, this is the foundation, we call it raft. You know, what is raft? Yeah, equipment is used in water to carry heavy weights, so that it actually, it floats. And there's a lot of woods are tied, logs are tied, and that over that you keep the heavy weight. So what we call it, it is a raft. Raft is another name is barge. So it is now the raft. This raft technique that used about 1,000 years back. The raft's main function is distributes the load evenly throughout. That was, see, when a load comes down, when the load is transferred in a wider area, it distributes, and the earth is able to resist the load. That is the concept of it. So each in raft they had used stones. That stones to a length of about 3 meters, 2.4 meter, or 45 into 45 centimeter into 60 centimeter. This type of stones were used in this. So foundation's function is to distribute the load. That is why the foundations are wide at the bottom. Another example for this, I can tell you, you take a crowbar of 15 kilos, take a rammer of 15 kilos. Rammer bottom will be about 20 centimeter 20 centimeter into 25 centimeter. The crowbar is very sharp edge. You drop it from an equal height. What happens? The crowbar penetrates more. The crowbar penetrates more. Why it penetrates more? The point load. The point takes all the 50 kilos. So load divided by the area, you get per square centimeter, square unit, how much the load takes. The same way the ramp, the total area 20 centimeter into 25 centimeter. That whole area takes that 15 kilos. 15 kilos divided by that square unit, you get per square centimeter what is the load. And if the load is less than the resistance, it's able to stay more on top. These principles have been used in foundations. So now coming to the structure. See, this is what we call it, jamb of the entrance door frame, door jamb. See, this is about 40 feet by 40 feet height, and it is the 1.2 meter by 1.2 meter square section. And it is placed vertically, and there is another beam-like thing, it is placed, that we call it post and beams. These were the first structural element made by human species. Everywhere, whichever the country they started using a vertical element that will be supported by a horizontal, that supports the horizontal element. So that horizontal element is the total load is distributed by that, and half the load of this horizontal element comes to this column, this post, and half goes to here. So that is how it distributes. See, you can see the column here. You can see the column here and the beam at the top. And other places, when they wanted to reduce the opening, they used a technique called carboling. It is cantilevering. Cantilever. Normally a cantilever principle, whatever the projection, whatever the weight here, that should be 1.5 times at the back. If it has got a 1.5 times the rock, then it won't topple. It won't topple. So you can place this and go for another rock. By doing that, you reduce the opening and bridging this a gap at the top. That is, we call it corner. At the top, the projections are done. This is a technique which was elaborately used in this in this temple. Most of the temple in India, they have done this carboling. I just missed the word, carboling. This technique is called carboling. And normally the thumb rule is, if it is at about 3 feet, you can project 1 foot and place it. That is 3 feet in 1 meter. 1 meter, this is about 30 centimeters. You can do that. So that is how the carboling is done. And that time we never had any IS code and other things. It was done with an experience and thumb rules. See, the entrance opening is reduced by introducing another element, vertical element, and at the top it is made into an arch. See, this is a buttress supporting so that it doesn't shift this side or that side. This was done by British to reduce the opening, to give safety and security to the people inside. See, the top door. Even if you can open this, you don't have to open the top. See the carboling, you could see this. See, this is a projection. This projection backside, it goes up to this, up to this, up to this. So the weight of projection is 1.5 times at this point. That was the thumb rule used by many of the temple architecture, and it still says. 1,000 years. There is no settlement, no cracks. And this temple has got a very special technique. There is no mortar between the stones. It is placed one over the other. The technique, they call it cup and joint, tongue and groove, all those things. See the stone. The stone, it goes up to, say, single stone placed on this. And the opening is approximately more than 6 meters. You cannot get a stone lintel to keep it like a beam. So they've reduced it and brought it to less than 6 meters, 4 meters something, and they have placed a stone. And here you can see, as I said, there is no joint mortar in this. It is placed one over the other. See, this is standing because of compression. There is no tension at all. Only in compression you can do this type of things. In compression member, compression element. See, this is how tongue and groove. And ball and socket. This is a ball and this is a socket. This to reduce the lateral movement. Another tongue and groove, straight line. And this is a interlocking system. All this done were in stones. See, this is another. See, you would have seen the big temple wall. The lines are not straight. The joints are not straight. That we call it polygonal joint. And there is no mortar. This itself gives a lateral, resistance. Nothing can dislodge this. This wall, this is a ball and socket. The walls are done like this. Again, tongue and groove. This is a tongue and groove, interlocking. See another wall. This is how they done it. This is nothing but from here only the Westerners have taken the clue. It is something. What is this? Lego blocks. It is nothing but instead of ball and socket, ring and lock. Rings. It will have a cylindrical projection and top will be a hollow and it will be tightly fixed. Building blocks. Now coming back, the compression, how it is transferred, the whole weight of the shrine, the tallest shrine, how it is transferred. See, this is a place where it was split. This is another compound. This is another compound. So the whole temple is in a concentric squares. The inner dimensions is 26 feet. And this is about 11 feet. And 6 feet is the corridor. And this is 13 feet. So concentric squares, the load is transferred. And there, this is a carboling. By carboling, they brought it to this level. See the beautiful cross section of this. And you can see the detailing, the side compound, what I said is one wall is 13 feet and another wall is 11 feet and inside corridor is 6 feet. See, there is a 2 layers, 2 tiers, and over that is a hollow structure. But see, at the top, it goes up to the top, hollowness, just below this. And see the load is how, it's a solid. It's only done something like a carboling only inside. And the load is transferred on this and brought to the 2 walls. And from the walls, it goes to the ground, raft foundation. The front mandapam, where you could see a lot of pillars and then the roof. See the inside carboling. It goes up. It goes up. And this is what I said. It's a polygonal joint. It's not straight line. Random it goes. Look at this. Another technology. Technological wonder. See, from here, from the support, from the column, it will be about 2.1 meters and more. And the whole thing stands. This is not wood. It's all stone. Carved something like a woodwork. And this is a support. This is a cantilevered support. This is a fulcrum, a beam. Over this beam, this sunshade that is placed or that. And the way the sunshade is fixed, we'll see the details. See, this is how. Bottom pillar, from their beam. This beam is anchored to the ground, the other backside column. And over that, there's a beam fulcrum. And in that, rest. And again, this goes up. To reduce the weight in a sunshade, they've removed this. They've removed this. It will be to the total length, and in between, they've removed up to that. So very thin layer of stone comes over it, and it rests like this. Technically, it rests like this. See, this angular. The first portion is single corner. Second one is angled. Little bit less. Only when it comes to the middle, it will be straight. Again, it will be angular. This is a highly technical work. I call it angular friction. Due to the angular friction, this stands. The whole thing stands. It is done 1,000 years back without any technical machines or anything. See, they had the mind, they had the wisdom, for load distributions and other things. Look at the cornerstone. One is at the 45 degree. This is directly to the east towards north. And this is 45 degree. Look at this, how it is. This is one unit. And this is another unit. This is another unit. That it is assembled. It is something like woodwork, but it is not woodwork. See the giants, 1,000 years it has been standing without any mortar, like this. See this. See, this is a separate unit. This is a separate unit. Look at this. Now coming back. As I said, post and beams. How many of you seen this? This in Tamil, it is called Sumaidangi. Sumaidangi means a load bearer stone. Sumaidangi kal. See, this will be in a junction of a highway where a village road takes branches off. So when they come in a bus or in a vehicle, when they get head load, they take the head load, place it, and then take some rest, take it from here and walk to the town, walk to their village. From the village, when they come to the town, they'll bring the head load and place it and then take it. This is the best example of posts and beams. This is one of our early inventions, nearly 1,000 years, these inventions. This is a typical structure where that functional identity is same. Now also we have, and olden days also that was there. So this is very important basic structural element. Now coming back to this, this is a Nandi Mandapam, which was done about 650 years back by Nayaks. See, this is a freestanding column. On that a bed block, and over the bed block there is a beam. There will be something, another beam like that, another column, and that will be connected by slabs that acts like a roof. Here also same way. The beam, see, connecting being here, connecting that column, in between the stones are used like this. Look at this. The column doesn't come from down like RCC, what we do. So this goes up. It is placed on a stone block and it stands on its own by gravity. Perfect plumb to the plumb. And you see a bed block and you see a beam here and beam here. And the same way there is another column on the other side. So there is a beam connecting them. Connecting these two beams, we have stone slabs, small slabs. Width is about 75 centimeters, at the most 75 centimeters or 60 centimeters. So like that. Over that, weathering course is used. This is the best example of posts and beams. As long as there is no tension, the structure doesn't fail. See, that this is a compression. This doesn't take, that there is no tension at all. Because the depth is more, the span versus depth is very important. The depth is more, there won't be any deflection in that. So that is the reason our stone temples are still intact without any failure. See, this is another column. See the decorative, these decorative motifs to bring the projection like cantilever. At the same time, they conceal it with the decoration. It is a cantilever. Still further it goes. So that's how they reduce the span and introduce a beam. The same technology we are adopting now. We are doing a lot of temples with a machine-made stones. See, like this. See, this is a bed block at the bottom. Over that, a stone pillar. And over that, another bed block at the top to take the load of the beams. And over the beams, we have either a vaulted roof or a plain granite slab roofing. This is how the modern temples are done with the traditional methods. The principles what our forefathers had adopted. Now we are doing it with the modern materials, with the modern machineries and tools. We are adopting the old system. The same has been adopted by an European firm that we call it the firm by name Teamage. That is in India. Chennai Silks is doing that Teamage work. Here you can see the columns. See, you can see the column rods in the floor. Up to the ground floor, regular construction is done. And over that, the double rods are left. And then the columns are cast at different places with holes, 6 holes on that. And it is inserted on the rod. And the 3M paste and acrylic paint, a chemical, a glue is epoxy, not acrylic, epoxy. Epoxy glue is inserted, and this stands. And over that they go for a beam. This is something like a stonework done by Rajarajan, but now it is done modern, in a modern way, with modern materials, and they do the work very fast. The material is cast at different places. The elements, they bring the elements by truck and fixes it on the places. This is modern technology, using modern technology, doing the traditional work. Very beautiful, adopted. So what I say, Rajarajan has done 1,000 years back what we are doing now. What we are doing now. Look at this, even the staircase is cast separately. The beams are cast separately. You'll see how the beams are fixed. Staircase. See the column, see the beams, and over that slabs. The precast element. See, I said the double rods, over the double rods, they place the column and grout it with the epoxy-based glue. Through these holes, under high pressure, they apply the glue. And that the column stands upright. And in this, they place this beam. And over the beam, they put the slabs. Look at this. This is a column. This is a beam, independently. See, look at this. Look at this. The precast, the technique we call it precast. But what Rajarajan has done in stone, they are doing it now with the precast technique. It's nothing. Only the material shift is there. Instead of stone, we have a amalgamated stone chips, sand and cement. We make a compound. We pour it over a reinforcement and make a beam. But originally it was like a just stone. The depth was more. The depth was more. To take stone, depth was more for the span. But that time we never had the equipment to lift, so they didn't do that. They introduced a column in between, and they took a stone of this size, placed it. Now we have a crane facilities from where somewhere we can bring the precast element, place it here. See, look at the structure. See the holes here where the double rods will be fixed after fixing. You know, about nearly, normally you students, you don't understand, you won't be able to understand the area, but to just take it, it will be about 1,50,000 square feet area, the plinth area with the 6 floors. They'll complete it in 3 months. So fast. A 1,000 square foot house normally takes 1 year. 1,000 square foot. Look at this. Then imagine the time span and speed, what type of materials used because of the precasting technique. See, now see some of the world wonders. See, this is Burj Khalifa. The plan itself distributes the load. The wind velocity, this resists. And if the wind is this side, this arm resists. And as it grows higher and higher, it gets reduced. So wind resistance gets very minimum at the top. And this is another, it was, before this was the tallest building, Burj Al Arab. This was an iconic building for Dubai. All the number plates of the cars, you have this. See, then coming to Petronas Towers in Malaysia. This whole structure is enclading by stainless steel. Initially, inner will be RCC structure. Over that, stainless steel cladding is there. And it is connected by a suspended bridge. It is not connected to this side or this side. So any tremor, even the building shakes, nothing will happen to it. See, another is wonderful structures. See, now I've started with the traditional compression members. Now gradually shifting to tensile members. The tension members, if you maintain the equilibrium, you can do it. See, like this, the twist. This is also a structural part. Pre-tensioning. The best example is for that pre-tensioning. How many of you have the rope made out of coconut fiber? When it is single fiber, it's very fragile. When you twist it with 10 or 15 fibers, you get a thread very strong. Still, if you add on the strands, it becomes very strong. That is how they make that huge ropes to pull the temple car. Ter vadam, they call it. That is also a technological thing. They like it, again, twisting, pre-stressing. All those things are there. See, this has got a speciality. Each floor rotates on its axis. So nobody in the floor will have a constant view of one side. So it is circulated, it comes back. It in an axis, it rotates. So that's a new invention, and based on the rotation done with machines. See, here the cantilever arm is so big. The other side, it will have a balance. The center core takes the load of both. Now I think I have taken you around and given you how the transfer of compression member to tensile members. And initially, all the temple constructions are about 1,000 years old or 500 years old. All were of compressive member only. Compressive members only. Now, this modern structures are a lot of tensile members. All because of the materials available. Advanced steel is available. Advanced, even the concrete is used with a different combination to increase the strength. Tensile stress, compressive stress, all those things. So it is the development is there, but at the same time, the traditional wisdom still lives, and it is able to cope up with the modern technology, the advancement. So that's what we say. The basic principles are same. Only the materials adopted are different. Okay, I think with this, I wanted to conclude with this structure, which has got all the technologies adopted in the modern buildings are there. So this, with this, I thank you all.
Thank you, sir. It was a
Right,
great session, sir.
Thank you very much.
Yes, sir. Now I would like to welcome Jeremiah for delivering the vote of thanks.
Yes.
Good afternoon, all. It gives me an immense pleasure to deliver the vote of thanks. On behalf of Department of Architecture, Periyar Institute of Science and Technology, I would like to thank Engineer Er.S.Rajendran sir for accepting to deliver the lecture on the basis of structure. Thank you, sir. Then I would like to thank our Dean, Dr. C.V. Subramanian sir, for encouraging us to work on the lecture series. Thank you, sir. Then I would like to thank our HOD, Architect N. Ramesh Babu sir, for encouraging us to work on the lecture series. Thank you, sir. I would like to thank Engineer Lata ma'am for arranging this lecture. I would like to thank all the department faculties for guiding us throughout the event and for participation. Last but not least, I would like to thank all the students, academicians, and practitioners of various organizations for your active participation. Once again, I thank one and all present here. We'll be connected with you in the future series. Thank you.